Come to the summer school. Today is second day. So today the first lecture will be given by Professor Mulders. Professor Mulders got his degree in the Netherlands University, and then he went to the Los Alamos and the MIT as postdoc. So after that he returned to Netherlands, working in the NIKHEF, National Institute for Subatomic Physics. Okay, and then he moved to the Free University of Amsterdam. Actually, the V is I try to use Google Translation. It's on Belgium, but it's really too difficult. But it meaning is Free University Amsterdam. And actually, if you can find that one parton distribution named after Professor Mulders. It's called Bohr-Mulders function. So we are very, Professor Mulders is expert on many things. In particular, he has a lot of pioneer work on transverse momentum dependent parton distribution. So we are very happy and honored to have him to give us the lecture on this topic. So let's welcome our speaker.
Thank you very much for this kind introduction and also for the invitation to lecture here. It's my first time in this country, and yesterday already Dr. Kao gave me a complete introduction of the history and also the role that the Dutch played in this, which I even didn't know about. Because I think, as usual, we are traders. So we go somewhere and then we sell it to somebody else, be it the Portuguese or the English like New York and that sort of things. But on the other hand, we also have universities and institutes. And maybe you didn't want to pronounce my first name, Peter, which is just the Dutch sort of short for Peter. Yeah, so that's, and actually this name also, not many people know that Mulders is just a Dutch form of what in English is Miller or in German is Müller, or so it has to do with mills also. Although, as far as I know, in my family there never was a Miller. But okay. Nevertheless, the S is supposedly son of, so it's I mean it's an offspring of Millers, I guess. So also on the universities, so indeed. Free university, although the university always says you are not supposed to call it free university because we do charge tuition, but it sort of was established as a university free of government influence and that sort of things. Although then later on it had lots of religious influences, but nowadays all universities in the Netherlands have essentially a general educational system supported by the government. So that's this, and this the National Institute for Nuclear and High Energy Physics, that where the original K and H are standing for, has been renamed indeed the Institute for Subatomic Physics to make it even broader or more general, and that is already exists now also quite some time. And it's essentially a collaboration of several universities, among which also Nijmegen University, which was indeed the university I started off. So this is something background on myself. This is the Dutch funding agency and the European funding agency, which I profit of a lot. So that's on this, but the most important part is that transverse momentum dependent distribution functions. Maybe I should call, I mean, part of sort of my sort of love of symmetries and that sort of things comes back from my original teacher, Johan de Swart, who was essentially, I think, most famous for all the SU3 platforms that are in the particle data group, and which unfortunately has died in June at age 83. Okay. So I owe him a lot of credit on this sort of things. But, so let's get to the physics. Transverse momentum dependent distribution fragmentation functions in high energy scattering processes. Now
Sorry, can you move the microphone
a little bit closer so that the...
Maybe up a little bit.
Okay, I'll move it up. This is better. Is it better? Yeah. Okay. So I essentially, this material is on my webpage and it will be also on the school page, I think. It's either in a big file of all the lectures, although of course I never know where I will end up in these lectures. But we'll see how far we get, and otherwise I will modify them and we'll see that what is on the web is more or less what I also discussed. As I also, and for that let me immediately jump to was it. So if you go to my webpage and essentially scroll down a little bit, what you will see is at some point some talks, conference, contributions and lectures. And the upper one, the Clino masses and mixing, is essentially not something I'm really working on, but it has my interest, and that I'm teaching about next week. That's also why I had, for instance, problems when the school is somewhat extended, so I have to be back, and I can also not stay and look more at the wonderful country here. So this is essentially what I will talking about, and these are the slides. And there is something which is called background material, which is about a few hundred pages of everything. And it's for people who want to use it, be aware. I mean, some things have been written 20 years ago, and there have been some changes in sign conventions at some point. So always be very careful. But it is background material which could be useful. Actually, there are some parts which are simply ideas and which are not yet even published, but as soon as you think about it and look at it, feel free to contact me if you think about that sort of things. But it's many of the things relate to essentially what I will talk about. And it's, as I said, has background and all the details and trying minus signs and indices and whatever, because that's always, I like somehow for myself to understand things and then completely figure that out. But that's usually the hard part, which takes quite a lot of time. As most of you probably know. And interrupt when you have questions. Do interrupt immediately when you have questions. And if you not immediately want to ask them, do it this afternoon or at lunch or this evening or whatever. And I can try to incorporate some of the things tomorrow in what I'm going to say. Actually, these general things, which were lectures at the school in Varena, and even Alba was a school in Erice, and some of these might also be useful because they have other materials. So feel free to have a look at some of these things. Okay, so let's go back to the PowerPoint. Okay, so this is what I plan to address. So let's get to it. Oh yeah, let me introduce. I mean, many of the things I am working on with people in my group, and that right now is quite a big group with a number of PhD students. This is the group of PhD students. These two actually starting this fall, so really, that's thanks to an ESC grant that is quite a lot, and some postdocs from Sweden, Spain, Italy, China. And this is the one with Daniel Boer, who I am still at some points collaborating with. He is a professor at the University in Groningen, and he had his PhD with me originally. And Gember and Rita Okajé are simply collaborators in many papers. Some of the work are not mentioned. Okay, so that's this. So let's start off simple and realize that if you are talking about hadrons, that you know some things. You know they have masses, they have charges, they have spin, they have a magnetic moment, and then already it gets more complicated, and you see not one or one half or whatever, but more complex numbers. They have isospin, they can be assigned isospin, strangeness, baryon number, whatever. Of course, we know how to trace that back to a very simple picture where laws, valence, quarks play a role and then build a proton. So that's, now you should feel exalted to say, well, we know all of these things. But you can ask, you know a lot of things. These are essentially global properties, the mass. I mean, you put your proton on a scale and then you measure it, or do it slightly more complex and have charges and masses you know expect or whatever. But you can measure these things without worrying about what the object really is, because these have charges, notably, have very global properties. It cause an electric field, which is extending till infinity. Of course, you can have some ways of looking at the proton, and here I divided it. This is more for the introductory popular talk, sometimes for students. You can have a real look at it. Shine light on it, photons. What you see if you have photons and you have photons nucleons, you can excite the system. You get resonances, you get N stars, deltas, you get a whole resonance spectrum with growing energy. That already teaches us some interesting things. It teaches us that something you can excite, so I mean, it seems to have structure. And typically the spectrum of this is hundreds of MeVs. That tells you that, say, typically it's a natural excitation for objects which have a size of, say, 1 femtometer. So this is sort of the basis of getting this composite picture of nucleons. Now there's other ways of looking at it. I call it here a weak loop. A weak loop. A nucleon has of course is an isospin partner of the proton and the neutron. So essentially you see a neutron decaying, and essentially that tells you that there are other properties that play a role. We now know which properties, and we know that you can assign an axial charge, and that thing and coupling to the axial currents of, and actually we know of course it's not a neutron and a proton, we know it's the quarks that couple, etc. And that gives us information. So this, the axial charge, this number 1.26, is of course then in principle something which is not completely trivial, because if you just did it with spins and do this most naive picture of valence quarks combined to a nucleon, you would find that you would expect 5/3. And so 1.26 is then quite a deviation. So you see there are more complex things of the structure of a nucleon coming in already at that level. So this is not just a simple number to be understood like 1/2, etc. Just as of course these other numbers mentioned previously, the magnetic moments, which are actually the ratio which is perfectly in agreement for going back the ratio here, the ratio of magnetic moments being, what is it, 1 to 2/3, with a change in sign, is of course in perfect agreement with this naive picture, but the numbers itself, of course, have some information. And again, they do also have this information on, say, the size of massless fermions hidden, say, in a cavity. That was the MIT Berg model, which I also career played with at some point, and essentially gives you a natural interpretation of the size of these numbers. Okay, you can go on. Not have a real loop with photons, but virtual loop. And then your photon could be a virtual photon, which could either be a photon which is time-like, produced in E plus E minus, or which is space-like, being exchanged in scattering an electron of the nucleon. Actually, if don't feel embarrassed if you this afternoon or whatever, or I will not do it on the blackboard, that will take too much time. If you say, oh, you know that this is space-like or time-like. I mean, some of the analysis maybe I think within the first exercise indeed we show that this sort of annihilation and that this sort of scattering will lead to that this momentum Q is Q squared positive or negative, always positive in this situation, always negative in that situation. But I think most of you may have seen it, or yeah, you've seen it in basic courses of, and otherwise just discuss and ask. I mean, that's something I may have forgotten almost how it goes, but it's basic, these sort of things. Okay, so this virtual look, so you can have, and then essentially you see essentially again structure reflected. Somehow, without doing something to the nucleons, of course there are regions which you couldn't even get to. And then this region, space-like, of course, yeah, that you can get for any space-like, and it depends just on the scattering angle of the electron, how large Q squared is, or how negative it is, what minus Q squared is. So it can start at 0 for Q squared to the negative, and then essentially it drops off. And the interpretation of this drop-off is something that has to do with the structure, and it's what is called the form factor. I mean, we saw it yesterday already. I mean, it pops up in every composite object, being it a nucleus or a nucleon. Substructure essentially tells you that this is not a point charge, but it's a distribution of charges, and so it will lead to form factors. And that's part of a bigger thing of such a coupling. It also has time-like pieces, which you, for instance, in the production of nucleon, anti-nucleon, or in anti-nucleon annihilation, you can sort of get access to that region. And then the intermediate region, yeah, you have to do something, you break up things, starting with NM bar. This might be the thing that's going through a photon, which now is time-like. It could be sitting at a particular mass, and if this mass happens to be the whole mass made up of a quark, anti-quark, and decaying into pi-pi, that process is quite dominant in a certain region, and in this way you can get information on such form factors or whatever the precise object is. So that's another thing which in many of these situations people usually step over and say, that's how do you parameterize the thing in a model independent way. And form factors are a very nice example of, say, a model independent description which can be used, and for which of course an experimentalist immediately can measure, and he says, here is your form factor, and then the theorist can go to a separate room, can sit in his or her office and start saying, and I can explain this. And then you can come back and talk to each other and say, I cannot explain, I can explain it, but you see at large Q squared it should behave like this. And then the experimentalist can of course go back to his lab. So the nice thing is, to make this story short, is that you need all these objects where people can talk to each other, experimentalist and theorist. And going back to the title of this, distribution functions and fragmentation functions are precisely what some objects that do this. Okay, so this is about the virtual, this is interactive, you say. And so they give you information. Actually, they don't give you too much information. That was what I was trying to emphasize already. Like the global loop, you see something. But for instance, they give you something. There's something that couples to a proton and leads it from momentum state P to P prime. And then you say, but this structure, being that these are fermions, and this is a certain operator which has a certain property. For instance, it could have, if it's an electromagnetic current, it would be J mu. That's much more obvious. You more often see J mu between the P and the P primed, and then it's parameterized in terms of two form factors, F1 and F2 of Q squared, or GE, and the electric and magnetic form factor as a function of Q squared, and then delta always often written as Q, the difference of this momentum. So, but it's this thing, if this thing would not have any shares, essentially it would have this behavior, and that's purely because P and P primed are momentum eigenstates. And essentially this is something that couples and for which we are using, and that's another thing that in all these lectures will come back in distribution and fragmentation functions. We are essentially saying we know the theory. The theory is QCD. We are working with operators and we are working with currents and whatever, and they are expressed in fields, and we know the basic field theories. So often we know lots of things about this, and in particular this behavior, and if it doesn't have Lorentz or Dirac or whatever indices, essentially you say, no, not much can happen. The translation invariance tells you that this thing between momentum eigenstate must be of the form e to the I delta x, where delta is the momentum difference, and then there can be only functions that depend on t, where t is the delta squared, because that's also information in here, so the x dependence we have, translation invariance, and then the only invariant that you can make here is delta squared. So the momentum transfer squared. And that's then these functions can depend on. And of course there could be a function which then doesn't have indices, but because you do have the momentum in principle available, it could depend on the momentum, delta mu, with its indices, but then there must be an invariant function which has a mu index. So these are two properties that you would get for a scalar operator. And that this would be the equivalent of the well-known sort of parameterization of the Nucleon current in terms of form factors F1 and F2 or GE and GM for a scalar object. Now, ion, no, not ion. That again, then you spin of these would also not very well. So that's the object. And of course, now what you see is that what is this thing? If you take it at t equals 0, you have more or less a property of the proton. And this operator is then this. The x dependence doesn't matter, it's translation invariant, so it's 1 at 0. And this is, if you want, this is just a charge, and if this would be the electromagnetic operator. So charge, mass, axial charge are all examples where this operator is then either the J mu of x, so the electromagnetic current, it would be the axial current J mu A of x. I'll show those currents in a minute. It would be the mass. If this operator would be more complex, it would be the energy momentum tensor, T mu u, and it would be parameterized, lots of Q mu's coming in. I mean, if momentum transfer plays a role, or even P mu's coming in, and it has a certain structure, but the number that comes in is then m squared at the point where this and that momentum is the same. And then already, that's actually a little bit, it could be an exercise. So maybe I want to, if whoever is interested, I'll go through it, but I'll do that this afternoon because I already go slower than I expected. You can take the derivative with respect to q and then go to q equals 0. And then the nice thing is that you can see that this g2 mu or at the point 0 is actually also a static property. The static property is essentially this operator, x mu O of x. Where you have to be a little bit careful how to define this x and whatever. You have to choose if you want sometimes a certain frame, but you can do it Fourier frame independent. And that certainly, I mean, it essentially tells you that operators that would have the position in it, and there are examples. Magnetic moments, which are essentially R cross J, or angular momentum, R cross P, and field theory. Of course, we know what P is, that's the energy momentum tensor, so components of it. And so R cross P is an operator of that type, and what you see is you cannot measure it at delta equals 0, because it comes in a piece, in a parameterization, which multiplies delta mu. And this is why angular momentum, for instance, cannot be just a forward matrix element, but you really need the P prime. And now already I tell you a secret, or maybe not a secret, distribution functions and fragmentation functions will also be cast in this format of operators, but they always will be forward matrix elements. And then for instance, that allows us to measure charges and masses. There's experiments that can measure the number of quarks minus the number of antiquarks. Hopefully some of you know what it is. Spin you can measure in deep elastic structure functions. Just using forward matrix lines. With angular momentum you cannot. So you have to go to all the new framework. That's what GPDs is all about. Isn't it, Marcus? That's short. But I think that's very important to realize that certain things you cannot measure simply in forward matrix elements. Okay, so that you will really need the scattering. And elastic scattering, of course, at some point, it always falls off because the object only has a finite size, so it's always form factor damage, and so things go down. But the nice thing of distributions of fragmentation functions is that they will be forward matrix elements, which in an experiment also show up without any suppression. Yeah, if you do deep elastic scattering, there will always be a lot of Q squared, but there will not be additional form factors, which usually fall off as much higher powers of Q squared. So that's on the some aspects, general aspects of this. And so in this way, form factors have taught us beautifully about the densities. Recent JNAP experiments have given us beautiful pictures where the density, the proton, and also even neutron densities of neutral objects can be measured in just elastic scattering. That's all the topics, so I will just skip most of them. Yeah, I mention again one thing. These are global properties. And you see here the neutron density, positive, negative, as a function of translated into R. That's the Fourier transform of these functions g of t. They can be interpreted as the charge as a function of x between the proton states. So essentially you can translate it into densities in a natural way, space-like densities, because the momentum transfer in that region is space-like, and also the x that you measure is space-like. So you have here these beautiful space-like densities, and you see the neutron being positive, negative, but that doesn't tell you anything about its structure. It tells you a global property, that's the charge distribution. It doesn't tell you if the U, the positive, if an up quark sitting more central than a d quark, because the d quark is negative, maybe the d quarks are on the outside and the U is on the inside. But maybe there's anti-quarks. And this seems to be the, again, when you go to deep elastic scattering and see something on the quarks, maybe it tells you that there is a basic thing that U and D are identical in the proton or in the neutron. And so that doesn't, that cancels, they have identical wave functions, both are more or less massless in a massive object of a proton or neutron. And then there's another component which is proton pi minus. And then the proton is heavier than the pi minus, so then it may be natural that the pi minus is much more extended and the pion fields on the outside or that sort of thing. And okay, that seems some picture. A little bit of proton pi minus. But to put it, that's theories that come up with certain ideas. This is how the proton structure should be. And experimentally, you can measure this function. It can give you this charge distribution. You cannot decide purely on the basis of such a measurement if which of these models, U more central or proton pi minus component, would be the right one. Okay. Now, of course, all these currents are given the framework, as I said, that we do have a framework in which these operators play a role. We know quite a lot about these currents. These currents are essentially the currents that interact with photons, W's, Z's, or whatever, and these currents are, of course, very well known in the field theoretical language of the standard model, and they are just essentially for photons. They are the vector currents, the Q bar gamma mu Q of the Fermi